Alright, so in this video we're going to review how to solve for the specific solution to a second order ODE, and the way we do that is apply boundary conditions. Okay, so here is our second order differential equation. So this is the most general form, and so let's say that you've gone through the process of solving for the general solution. It may look something like this. And so this is a very general form, and so you maybe might have some function f0 of x, then you have another function f1 of x multiplied by c1, then you have another function f2 multiplied by c2. And so this may look very foreign, but I had to make this as general as possible because these functions can take any form. But once you reach this point in the solution, the key is here is you need to solve for c1 and c2, because these constants as of this point are completely arbitrary, and we won't be able to solve for the full solution until we specify their values. Okay? And the way that we usually solve for these constants is by applying or forming two algebraic equations to solve for these two unknowns. And where those algebraic equations come from are the boundary conditions. So physically, what boundary conditions represent is that they describe how the solution behaves at the boundaries of the solution domain. And so some examples you may see in mechanical engineering would be maybe the temperature at a fixed location, or maybe the pressure at the end of a rod if you have a structural application. Okay. And so for a second order ODE with two unknown constants, what you need are two boundary conditions to fully specify the solution. And so for most of the problems that you're going to deal with as an engineer, they come in two different flavors. And so one type is called what I like to call function type. Its formal name is Dirichlet boundary conditions, which is given by this form right here, where you specify the value of the solution itself at a specific location. The other type of boundary condition that you might have is what I call a derivative type, the formal name for that being Neumann boundary conditions, where you specify the value of the derivative of the solution at a given point. Okay. All right, and so with a concept like this, where it's really a process that you have to follow, I think the best way to learn this is through an example. And so I'm going to do an example here, but I want to make a note. And so I'm giving you this example to illustrate the process, right? And so you can see here that I've given you the general solution as well as the boundary conditions. Okay. What I see a lot from my students is that they look at an example like this and they copy just this exact formula, those exact boundary conditions, and I don't want you to do that. Okay, remember that we're illustrating the process here, and so if you're solving a different ODE, then you're going to come up with a different general solution, and most likely you're going to have very different boundary conditions as well. And so you can use this example as a reference for the process on how to apply boundary conditions, but please don't copy these exact equations, because that's going to give wrong answers, and I'm going to have a lot of angry professors in my inbox, which is never a good thing. Okay, and so here's our example. So our general solution is minus 1/6 x cubed plus c1x plus c2, and we have our two boundary conditions here. Okay, and the goal of this example is we're going to solve for the values of c1, c2. Okay, and we're going to do that by applying our boundary conditions. Okay, so let's start with the first boundary condition. And so the first boundary condition says that dy dx at x is equal to 0 is equal to minus 6. Okay. So let's start with our general solution here, and then let's first take a derivative, because this is a derivative type boundary condition. And so if we take the first derivative of this, we get the following equation. Okay. Notice how we eliminate c2 because it's just a constant. Okay. Next thing we're going to do is that after we've computed the derivative, we're going to evaluate it at x is equal to 0. And so everywhere you see x, we're going to plug in 0. Okay. And so we have minus 1/2 0 squared plus c1. And if we evaluate that evaluate the math behind that, all we get from that is just c1. Okay, so now we've figured out the left-hand side of the boundary condition, so we can go ahead and plug that in. Okay, and so what we found is that dy dx at x is equal to 0 is equal to c1, and so we plug that into our boundary condition, we get c1 is equal to minus 6. Okay. Now that we've applied our first boundary condition, we're ready to apply our second one. And so our second boundary condition is y at 3 is equal to 18. Okay. Once again, we're going to start with our general solution here. But before we start plugging in for x, let's go ahead and plug in for c1, since we just found that out on the last step. And so we said c1 is equal to minus 6. All right, so now we can start plugging in for x. And so this boundary condition specifies that the x value is 3. And so everywhere we see 3, we're going to go ahead and plug, everywhere we see x, we're going to plug in 3. And we evaluate the arithmetic for that, and what we get is minus 22.5 plus c2. Okay. Now that we've evaluated what y of 3 is, we can go ahead and plug that into the boundary condition. And so what we get is minus 22.5 plus C2 is equal to 18. We just moved the 22.5 to the other side. And what we get is C2 is equal to 40.5. Okay? And so from there, we can form our full solution. And so we've solved for the values of C1, C2. So let's go ahead and plug them in. And what we get is a full solution of y of x is equal to minus 16x cubed minus 6x plus 40.5. Okay, so that was a very quick example, also a very simple one. And in fact, we were able to solve for each of the constants basically one at a time from each boundary condition. But what can happen sometimes, depending on the problem, is that you might run into a situation where you apply one boundary condition, but the equation that you get from that has both C1 and C2. Okay, and so you might get a system of equations that you see at the bottom. And so in these situations, you have to solve kind of both equations simultaneously. And so you can use your favorite method for solving systems of algebraic equations. And so you can either use substitution, you can use cancellation, whatever you need to do to solve for C1 and C2. Okay. All right, and so that concludes this refresher on how to apply boundary conditions.